Live? This is like, ah. Live? This is like, ah. And we're live.
Philip, I very quickly try once more to share the slides because I rearranged all my windows. I just do it very quickly.
Oh, there are intruders.
Okay, this way you would see the slides, do you?
Yeah, we do.
Yes, we do.
Yes, okay.
You can also full screen, then you don't see the control, but other than that, it's all good.
If I go, let's see. Oh, but then I don't see. Yeah, then I don't see them. So I like to.
It's fine.
Yeah. Okay, I'll stop sharing and then. Mhm. Mhm.
So Uli, we can hear your conversations just.
Yeah, sorry.
But they're okay.
Sure.
Try to be okay. My daughter is still here, but she doesn't want to be on the video. So.
Yeah, I may have my son or daughter like passing by.
Traumatized and then run away.
But Lorenzo, you're in the office now, so no kids behind your back.
Hello, everybody.
Hi, Ingo.
Hello, as well.
So, Julien.
So maybe we start like 2 minutes after, maybe? Are you fine? Yep. People are coming in. So, Philippe, you're responsible for letting people in?
Okay. Yes, I will shut up because I'm completely overloaded with technology at the moment. But I'll try and keep everything running.
Okay.
I mean, you can just open the waiting room, right? So then you don't need to leave people in all the time.
Yeah, I'm also working on the live stream and everything else. But yeah, and tweeting live.
No, it's like a radio host with a nice microphone and the headphones. I think you have a future in the radio hosting, for sure. And also you have a nice the trees. There's the green leaves, very nice. Like
I'm living in a video studio now, right? Thanks to Corona teaching.
Oh. Okay, so we start in 1 minute. Okay, are you all ready to go?
Yep.
Okay, so welcome everybody. So we are here in an event organized by the ELLIS Program on Theory, Algorithms, and Computations of Modern Learning Systems. So this is one of the programs of the ELLIS coalition of many researchers in machine learning and associated fields in Europe. So this program is co-organized by Philippe Hennig and Lorenzo Rosasco and myself. And within this COVID times, we have started to organize some debates, okay, about various topics in machine learning, okay. And so originally the debates were loosely modeled after debating competitions, but at the end, this has taken a nice format where people discuss questions related to machine learning. Very important point, the debate has to be courteous and cheerful. This is very important. And we can have disagreements, and I'm sure we have some, but this has to remain always very nice. And the debate for today, the question is, deep learning has made all other machine learning obsolete. So it's a question that we are going to ask. And so, so this is clearly a controversial statement. And we're very happy to have two leading figures that have agreed to organize this debate. And at first, we asked for them to be there and present 10 minutes, and they took on a whole, much broader perspective to it by starting a whole Christmas story. Maybe you can start to put the slides, Ule. And so those two speakers are Max Welling from the University of Amsterdam and Ulrike von Luxburg from the University of Tübingen, who are two leading figures in machine learning. And so the way it's going to be organized, the story will start with Lorenzo Rosasco as a narrator, and then the debate will be open to everybody. So please ask questions after Ule and Max have finished. And now the floor is yours, Lorenzo.
All right, so I'll just go on. Max and Ule sitting in their armchairs in front of the fireplace, thinking of good old days, of the ghosts of the ML past.
Well, Max, can you still remember in these old days in machine learning? I was much younger. I had still brown hair. I was a PhD student. At that time, it was so cool. I mean, people were interested in actually generalization bounds. You could prove theorems and people wanted to look at that. And I mean, the latest things were support vector machines and kernels and all these kind of things, large margin methods. And the papers I wrote, you could do something very fancy with functional analysis. You could write a NeurIPS paper that is about some large margin classification, and I used free Banach spaces. Does someone know what a free Banach space is? So that was such a nice time. I would really love to be back there.
Yeah, those were great times, actually. I also had red hair still by that time. And although I didn't work on free Banach spaces, I would certainly like to work on very shallow deep learning called independent component analysis, or actually on infinite models or culinary processes like the infinite Gaussian mixture model or the Chinese restaurant process or the Indian buffet process or infinite HMMs or infinite mixture of experts. Those were really the days. In fact, I think if it's come to think of it, Redford Neal already had a result that said that a neural network is like a GP with an infinitely wide layer. So maybe, I don't know yet, but maybe they already had infinitely deep neural networks back then.
Well, actually, I don't really know, but I remember 2012 when everybody started to talk about deep learning. And at that time, I mean, neural networks had been around since the 1990s. Everybody knew about them, and I didn't really take it serious. So as a theory person, you could just say, let's ignore that. I mean, that's going to be this empirical stuff. We are not going to care. In the meantime, it got a bit harder to ignore all this deep learning stuff, but then it was still very safe.
I don't want to be annoying, but actually it started in 2009, Ulrike. So not in 2012. So actually in 2009, there was the first sort of discovery that deep learning could, decrease the error rate of speech recognition. I think it was Microsoft that did it with Jeff Hinton. And, after years and years, maybe a decade of plateauing error rates, suddenly with deep learning, the error rates started to plummet. And a year later, we actually had speech recognition on our phones. That's when it was really started to become cool.
Stop
So
rambling
Scrooge,
about the past.
we can't see you.
Yeah, because I forgot. I was only talking, but I forgot I have an attire. Stop rambling about the past. Get to the ghost of the ML present.
All right. We'll talk about the present. Well, if we talk about the present, basically all success stories that you read in the newspapers are about deep learning, right? There's AlphaGo, AlphaZero afterwards. There is basically in 2012, actually, there's the ImageNet competition results where the error rate started to plummet in 2012. There's Dota, which was the game which was won by a deep learning system. So really, who still cares about SVMs or symbolic AI or actually anything else in life, really? And why did it all happen? Well, it's really bigger is better, right? If you make your system bigger, if you add more data, if you add more parameters, if you throw on more compute, the system will keep performing better and better. So we're now at 175 billion parameters for GPT-3. Basically, all of internet is sort of used as data. So basically, repeat after me. We just need more data and more compute, and that's it.
Are you crazy, Max? I mean, we're all machine learners. This is deep learning. This is just crap. They do all these engineering tricks. They train all these huge things on data. They don't control the data. They don't really know what their architecture does. It's just a bunch of engineering tricks, Everybody could do that. I mean, you just have this huge GPU rack in your basement somewhere, and then everybody can do it. Obvious things, that you have tons of data, you have all this power, then sure, you can find out all these things. So that's really boring. I would even say, it's close to cheating. This is not science anymore. This is just engineering, and people are building that stuff and selling it as if it would be the future. And the worst thing about all of that is it uses so much energy, and we're all in the Fridays of Future movement. And now everybody tells us you're supposed to use all these deep networks. That's really crazy.
All right, Scrooge, be serious.
All right, let's be serious then. Define what deep learning really is, because of course, everything else in AI, it's a container term. So let's define it as differentiable computation, like the differential neural computer from the Graves 2016 paper. All right, so basically any differential architecture that you can build, which could include discrete variables as well. But as long as you can backpropagate through it, and as long as you can learn the parameters of that huge architecture, right? And this includes CNNs, ResNets, deep RL, models such as GANs and VAEs and flows. And actually, it also contains one layer shallow, very deep neural networks too. So generalization then, right? So what is really interesting about deep learning is that people have found that there is this double descent curve now, which means that where we thought that we were overfitting when the number of parameters was about the same as the number of data that we had, if we start to over-parameterize and add more and more and more parameters to these networks, in fact, they start to generalize better, which is, truly interesting. And we have also found that transfer learning works really well with these deep neural networks. You can train on your vacation pictures and your family pictures, and you take that neural net and then you apply it to, for instance, melanoma detection or some other medical data, and you only have to fine tune a little bit and you'll get great results.
You know, I mean, do you really think that's true? There's this paper that came out just a couple of weeks ago, where lots of people who you think would know a lot about deep learning, like people from Google and lots of well-known places, essentially write deep learning currently is going to fail because you train all these models on very specific data. You find a model that has very great generalization capacities on your particular task you're trying to do it. But then if you try to deploy it in the past in an actual real world setting, it doesn't work. And you just need to read the abstract. It has poor behavior when it's deployed. You treat all these equivalent models on the training data, you treat them equivalent, but then in the end, they all do different things. So there are distinct failures and nobody understands really what is going on or how you could fix those.
Well, we haven't really explored everything yet, or we start in the beginning yet. And what's really important is to acknowledge that there is a huge amount of data around that we are really not using in most of these deep learning networks. These are mostly supervised learning methods that you have discussed in your previous slide. But really, it's in the end, it's all going to be about unsupervised learning, or as Jan LeCun likes to call it, self-supervised learning, right? And basically, you know, we don't need the labels. We just need enormous amounts of unlabeled data, which is the chocolate in the cake there. And in these generative models, you know, unsupervised learning and they train these generative models, we can stick sort of the causal relations and the laws of physics. So it can literally learn the laws of physics or the sort of causal relations. So we don't need symbols or symbolic AI or first order logic or any rules, or for that matter. We just need to learn and manipulate discrete structures through deep learning. And I also like to, you know, think a little bit about what actually is true intelligence, right? So let's take the human intelligence as sort of the role model for what true intelligence is. And I think one of the most important aspects of intelligence is that we are able to imagine all sorts of counterfactual worlds that will never ever happen, right? So like this person here who is imagining a blue elephant on a unicycle cycling on the moon, that will never happen. Yet these imaginations can really help us, you know, plan and reason about the future and about the world. And I just want to remind everyone that, you know, obviously this is all built in terms of neural circuitry because it's in our brains, right? And so I think when we build these models that can sort of, you know, project the future and unroll the future in a sort of a movie in our head, then I think we'll be able to do much better generalization. And in fact, causality can be learned in a deep neural network. So here, this paper by Cindy Lowe et al. It's a very cool and of course very deep, actually not so deep, graph neural network based variational autoencoder model, where you stick in sequences on one end, and then you have sort of a graph encoder module that predicts all the causal relationships, and then uses that causal relationships and, you know, all sorts of priors about how the world works, including sort of laws of physics, to then you know, predict the future sequences. And by just observing this, it can actually learn the causal structure of the world, which is precisely the way that we do it, I think.
Well, there are many people who think that that is quite unlikely to happen. And here I just wanted to cite Judea Pearl, I mean, who is obviously one of the people in the world who know most about causality out there. And what he says in this discussion is, if we want machines to reason about interventions, something like, what if we ban cigarettes? And introspection, what if I had finished high school? We must invoke causal models. I think up to here, everybody agrees, but now comes the sentence, associations are not enough, and this is a mathematical fact, not opinion. So neural networks are not going to be able to do that. You will not be able to successfully model all these causal relationships by just training a deep network.
Okay, well, I guess we could do it to some degree. So our neural nets do it. And so you can ask the question, you know, can computers actually reason about the world, right? And I would say, hell yeah, computers can. You know, for instance, AlphaGo beat Lisa Dole by doing a very interesting step in, you know, in sort of move 35 of game 3. That was, certainly reasoning about how to win, the game of Go. And according to Jeff Hinton, I think you can think of reasoning basically as an iterative application of sort of feed-forward deep neural network models that get coupled together in some kind of recurrent structure like an RNN. So it's like if the computations become too complicated to do with a single feed-forward neural net, you'll then have to start to iterate, right? And then if you iterate, you just apply iteratively these deep neural networks and sort of sequence the results. And that's actually what also happens in our brains, right? In the prefrontal cortex, you could think that something like that happens. And if that's not enough, I would say you can start to include sort of actual world knowledge in terms of knowledge graphs into deep learning as well. And of course, some people will claim that deep learning will never understand what they're really doing, like Gary Marcus. And then I would agree, not yet. Sure, humans have better world knowledge than our current best systems, which you could call maybe GPT-3 is. But you can ask, what does it really mean to understand the world, right? If we have a system that would perfectly answer all our questions, does it really understand at that point? Also, I think it's sort of a continual retreating argument, right? Next system, surely you'll be able to identify some things it can't answer, but it's getting better and it's getting better fast. And basically, the prediction will be with more data, with more background knowledge, with bigger models, and with more compute, we are going to get there.
Well, I mean, all these analogies, they're really tempting. And when you present it like this, it sounds really great. So essentially you say, humans have learned causality. So obviously deep learning can do it as well. So we have these deep networks, they essentially look like the brain. So the brain can do all these great things. So why wouldn't deep learning be able to do that? So, same thing with when you said imaginations are generated by our neural circuitry. Sure, that's true. And sure, it would also be true that if you have more data and more background knowledge in deep learning, you will understand more. But essentially, this argument goes in the direction of deep networks in the end, or deep learning, are going to generate artificial intelligence, true artificial intelligence. But the argument here is, look at the brain. The brain has all these neural circuits, and we are able to do all these cool things. We can do causality, we can do imaginations, we can understand things, no matter what understanding actually is, but we can do it. So it's just a matter of time that deep learning is going to do that as well. But here's a flaw in the argument, because deep learning is not a deep network, it's not the same as the brain. Of course, there are some analogies, but these analogies, I mean, if you talk to neuroscientists, they're very, very, very vague. I mean, we have a couple of neurons which are connected, but the brain is much, much more. And it is completely unclear whether deep networks will be the tool to achieve all of these things. Sure, you can say there exists a model, the brain, that can do all these things. So you cannot rule out the possibility that there exists another model, an artificial model that can do all these things. But the argument cannot be deep learning is going to do that. It might be, but it might not be. And in fact, I doubt whether it's going to happen. But this is not the discussion we're currently leading.
Yeah, so thinking about that, so the way I defined deep learning or deep architectures is as a differentiable computation. And if we agree that our brain is a differentiable computer in some sense, then the human brain falls squarely into that sort of framework. And I just want to sort of argue again that clearly, by definition, humans have reached AGI with only neural circuitry, which I would sort of, in my definition, neural circuitry would be an example of a deep learning architecture. And then you could still argue that individuals learn over their lifetime, but they get born with huge priors, and so maybe that's not fair. But then if you think the whole human race is also a learning system that learns over evolutionary timescales, right? So in some sense, you could argue that a neural network or a huge architecture that we can build could be distributed architecture, would need as much data as the entire race has basically ever seen, which is about 107 billion people times 40 years of existence.
Which is in fact maybe an argument against the hypothesis that we are soon going to build that. Anyways, let's come back to our question. So I think we drifted off a bit because we started to discuss whether deep learning is going to solve the problem of general intelligence. But actually we started off with the question whether deep learning has made all other machine learning obsolete. And maybe we should come back a bit more to the point that we've been starting with. So the first point in this discussion is, and that we have seen that already in lots of the graphs that Max has been showing, deep learning needs a lot of data. Now, there are many problems out there where data is abundant, and like in images or language or in many other applications, there is lots of data. But then there are also many other applications where there is not a lot of data, but still we want to do machine learning. And here I have an example from the geosciences where you want to predict, you can make certain soil measurements at certain places, and you want to predict the clay contents of the soil based on certain samples. And this is a real problem that people are trying to solve in many places. For example, if you want to build new structures, you want to know how does the soil change if you build these things, or if you change the landscape. But now in such a scenario, you can maybe afford to take 20 soil samples or 50, but not millions of them. So it is not going to work that you just throw your 20 soil samples into a deep network and you train a network with millions of parameters and it's going to work. This is in such an application, it's completely out of discussion. And a similar situation is true in very many scientific contexts where getting samples is really expensive. And if you just have 20 of them, a deep network is not going to work. The next thing in the same application that's also very important is there are many applications where you want to use machine learning, but you don't have a black box kind of thing where you just throw images in and something else comes out. You have a lot of prior knowledge. In this geoscience example, you have models of the world, you have models of the landscape, you have differential equations that tell you how I don't know, if it rains, how the earth is going to be washed down a slope. And you have chemical reactions that tell you if the sun shines on this soil, then it's going to change. And this is knowledge that humans have acquired over the last couple of 100 years. And you can't start machine learning and just say, you know, we ignore all of that, we just drop our samples into a deep network and we just hope that the network is going to rediscover all of these things and more on top. This is not going to work. So again, here, if you have applications where there's lots of prior knowledge that is needed to make this application going, then you will not be able to do that in deep learning. The next thing that comes up is in deep learning, essentially all the success stories are about classification accuracy. Sure, you can classify thousands of images, and the classification accuracy, at least on your test set, is really surprisingly high, and this is surprising. But now in real life, we often care about many other things, which are not just classification accuracy. And one of the things many people care about is explainability. And now, sure, there are some methods by which you can develop explainable models out of trained deep networks, for example, LIME. And this is really a great tool. What it does is like it says, here's a strawberry. So the algorithm tells you here's a strawberry, and the algorithm then tries to outline what is it in the image that makes a strawberry out of that. And for images, this works great. And this also works great, maybe for language, I don't know. But now the problem is this is a very local explanation. It just explains one local decision. And in images, this works. But if you have very abstract data, I don't know, gene expression data, where you don't have an image that you can show, it is really, I don't think that local explanations are going to be the ones that you need to satisfactorily explain what is going on in such a deep network. And in particular, in applications where you actually really care about the outcome, like in a medical application, which is not about images, but about different data, or in a social context, people, in fact, do not want to have deep networks with funny explanations, but they say, I rather prefer a simpler learning algorithm, but it gives me more satisfactory explanations. And somehow we can't ignore that. We can't just say, you know, we use deep learning and you live with the explanations we give you. Here's something that's a requirement from the applications that we should not ignore.
Hey, Ulla, let me just interrupt you with a random thought here. You mean the deep, interpretability is not just, for non-deep learning sort of models, right? So could we think maybe that consciousness, could that be the brain's attempt to explain deep learning with deep learning?
I think that question is too complicated for my small brain. Maybe we can discuss it later. But let me continue. with all the things that we might care about beyond accuracy. So another thing we often care about is uncertainty. Like in a medical application, I mean, no doctor is ever going to trust a device that gives you some kind of predictions if these predictions do not come with some notion of uncertainty. And one thing that deep networks are really bad at are trying to give calibrated ways or calibrated notions of uncertainty. Again, this is a place where I think deep networks are not, or at least a lot of work needs to be done before they would be able to solve this kind of problem.
No. We've covered our bases, Ule. It's called Bayesian deep learning, right? Or if you're a frequentist, you could just train another deep neural network to predict uncertainty. And by the way, can somebody please clean up the Reverend Bayes tombstone because it looks really ugly.
Okay, I think this is again distracting. So let us come back here. So there's yet one more thing we care about, which is not accuracy, it's not explainability or uncertainty, but it's robustness and security, right? I mean, since years, people are playing this game. Here is my next convolutional network, and some adversarial attack comes and we show it doesn't work. And then the people try to improve their network, and then the next attack comes. And currently, I mean, even though I know there are attempts to try to fix that, but the attempt, to my extent, to at least to what I know, I think they don't really work so far. So if you're in a situation where you really care about the fact that your algorithm is robust and secure, then deep learning is maybe also not the one that you should use. The last point I want to make is the inductive bias of deep learning algorithms. So there are many, and this maybe brings us back also to this paper I cited in the very beginning. So often deep learning algorithms seem to be really successful if you look on the surface, for example, in image classification. But now we are all theory and algorithms people, so we know that machine learning algorithms do have an inductive bias. So there needs to be something the machine is going to look for, but we don't know what it is. And there are many cases where people have uncovered that the inductive bias the machine is looking at is really not what we would expect or what we would actually hope to happen. So here's this one example that I want to show about image classifications, where people showed that in fact, what the deep network looks at is not the shape of the, so you want to recognize a cat, say, but what the network looks for is not the cat. It's more like the texture of your image. So if you use style transfer to take a cat, but give it the texture of an elephant, after that, the classifier is going to tell you this is an Indian elephant. And this is, and I don't want to use this as an example for showing that deep learning doesn't work, because it does successfully classify all the images in the database, but it looks for things that are completely wrong to our understanding. So we would never ever say this is a cat. This is an elephant, we would still say it's a cat. And similar things happen. I mean, you could now say, well, that's sort of images and that's maybe a bit complicated. But like if people try to apply these things, that happens as well. So there was this famous paper where people wanted to use in medicine, they used deep learning to try to recognize pneumonia from images, and they wanted to combine data from different hospitals and then carry it over to yet another hospital. And what happened is the classifier, like in each little image, there's a little token somewhere that identifies the hospital in which this image has been taken. And then the classifier, as a big feature, took what is the hospital token of this, where this image has been taken. And then there are some hospitals which have many more cases of pneumonia than others. And then, of course, the classifier goes completely wrong. But this is something that is not obvious. You really need to look into these things. But I find it very, what's the opposite word for reassuring and distracting or worrisome, that it would be difficult to figure out. So whenever you train a deep network, it's going to try to search for these things, which people now call shortcuts. And you never know whether the algorithm you trained just looked for a shortcut that is completely outside of what you've been looking for. So if you want to trust these things, I think currently it doesn't work. We need to understand, at least before we can trust it, how we can describe what is the inductive bias of that annoying classifier.
Audience enter the stage and takes over the discussion on the ghost of the machine learning yet to come. So your turn.
So thanks a lot, Uli and Max. I think this was very inspiring, and So I have to admit it's hard to disagree with any of you. Okay, so you make both very strong arguments. And so maybe it's time for anybody in the audience to either ask a question or make a comment. And if you do so, just please like put your camera on and speak. So I'll start with a question to get things going. And it's very like down to earth. Should we still teach regular machine learning? What is your take on this? You see sometimes people saying, with deep learning, you just need to know autodiff. So no need to know anything, just launch things, no need to know anything about like machine learning. Do you think this is like a good thing to do, or should we still like keep our teaching syllabus intact?
Well, if I can start, if that's fine.
Yeah.
Yes, so, well, about the teaching, so one thing which you realize when you look at those deep neural networks closely is that you actually notice that they are actually piecewise continuous function approximations, and then there's a link function up there. And then variational autoencoders are just using those piecewise linear approximations in a certain kind of way of combining them. So my question is that, okay, so is that going to solve all the problems in the world? Those piecewise linear function approximations. And so if you don't have a proper teaching in like a basics of regression and machine learning, you will never notice what actually is a deep neural network. So it's just a piecewise linear function approximation. Well, for sure, piecewise linear function approximations are very good, and those GPU-based teaching methods are very good in computing the gradients needed for the teaching. But well, so any comments? I don't believe that piecewise linear functions are going to save the world, but maybe others might.
Can I say one thing? Because I forgot to say that actually the role I played wasn't really my opinion. We should have said that in the beginning, but we both played a role, and it's far more extreme than our actual, much more nuanced point of view. But in maybe in response, my opinion is that yes, obviously we need to keep the machine learning curriculum as it is, and we need to teach lots of theory, and we need to learn people how to differentiate and all these kinds of things, and apply the chain rule and all these kinds of things.
Yes, and also like I'm taking the role of like defending the classical side indeed. So so if someone has like good arguments of favor of deep learning, though, that would be actually very good as well, because I can also find them.
I have one in favor of piecewise linear interpolation. So if you let the number of pieces go to infinite, you can do anything, no? So I think it's well known that if the number of neurons go to infinity, you can like adapt and get smooth functions. So I'm not totally opposed to like glorified piecewise linear interpolation. I think it may get you there, and I think the combination of it's universal and it's a combination of very, very cheap computational like primitives. I think for this, it's a very positive aspect of deep learning where you combine a lot of very cheap operations. And I think this, I don't know how you can avoid that. Okay. So
there was another interesting part in the discussion about the kind of fact about differential computing. And deep learning, deep kind of neural networks are definitely differential computers. But then there was a claim that brains would be. I kind of understand how differential computing works and how you optimize the system, but brains do not have a kind of a differential computing element. It is very hard to figure out how you propagate the error in a way that the differential computing does it. So I would say it's easier to understand the neural network behavior, deep kind of a artificial neural network behavior in the real brains. So how it actually trains and learns is, there are lots of claims about different ways of spiking neurons and this kind of things and learning systems, but this is not clear at all. So I would say that it is even more kind of a mystery how brains actually learn something about being AGI than how neural networks would do it. I would more expect deep learning neural network to reach AGI than brains itself. So how do you do it biologically if you just look at the technologies?
That's a fair point. Thank you.
Actually, sorry, I believe there's a proof showing that contrastive Hebbian learning subsumes backpropagation. Contrastive Hebbian learning being a biologically inspired learning rule.
Can I just say something? Two different, extreme ends of the discussion. So concerning what Francis was saying about should we teach machine learning instead of just classical machine learning, I definitely think so, because away from the media, I would say that most of the machine learning going on in, say, small, medium companies has nothing to do with deep learning. People are doing logistic regression, linear regression, clustering, classical stuff every day. And they still need to do that. And they're fighting data scarcity and unknowns and missing data and heterogeneity and lots of complicated things that need to be dealt with. And that deep learning is not yet ready to deal with. I don't know if you have the same experience. And at the other end of the discussion, at the brain, I think that Max already acknowledged that the position that he was defending was sort of a devil's advocate or God's advocate in this case, maybe for the deep learning. And he says somewhere that the brain is sort of a neural network, but the brain is, of course, a lot more than a neural network because we're forgetting chemistry. So there's a lot of chemistry in the brain, like neurotransmitters that are all around the cells, and there are things happening at different time scales that are not well modeled by circuitry. And so I would say there was still a lot, well, everybody knows this, but a lot more we don't know about how the brain works than what we know. So it's still very far away from that. But in the teaching side, I think it's very important that we still teach standard classical machine learning. I think it's fundamental.
I'm not sure everyone or whether Francis is noticing, but there are two people who have their hands raised, so maybe we should call on them.
I'm taking care of that. So maybe Suji, maybe to respond to Mario.
Actually, my question is about something that Max said that also relates to the piecewise linear question. And it's about the purpose of multiple iterations in reasoning. So Max said it's to make some decision that's too complex to make in one iteration. But I think technically, if you look at the polytopes, the number of hyperplanes or decision boundaries imposed on the input isn't increased by an RNN because the parameters in each iteration are the same and the input and the output live in the same space. So do you really think that the purpose of repeated iteration in the brain is to solve some harder problem? Yeah.
Was the question addressed to me or no?
Yes.
Yes. All right, thank you. So harder maybe in the sense of, I mean, so there's certain hard problems which get hardwired into feed-forward neural networks, like recognizing things in the world in one feed-forward pass. But I guess you cannot, those are probably things that you either use a lot, every second, and are therefore extremely useful, but you cannot get every task that you need to do sort of so solidified in some kind of feed-forward architecture. I guess you need to do it for things that you reuse a lot. Now, there's other things like adding numbers that we don't need all that much, right? And so I guess we haven't developed hardwire feed-forward architectures to do these kinds of tasks, but apparently we can do them by sort of iterative computation. And I guess it's for these sort of tasks that we use sort of iterative computation.
But an RNN unrolled is a feed-forward network.
Yeah, you can view it that way, but I would say it's in some sense, I would say it's more flexible in the sense that it's a recursive computation where you can. I guess it's more flexible in the way that it interacts and things like so. I would think a feed-forward net is just one thing doing one task all the time, exactly the same way, which is like audio recognition, vision, and all these kinds of things. But then I guess these things which happen in the prefrontal cortex, which is reasoning, it's a different problem every time. And so somehow, you can think of it as an unrolled, feed-forward neural net in some sense, but I guess there's more going on in a way in this recurrence. I don't know precisely what, but.
Okay.
Thanks, Max. So Marius?
So if I was defending deep learning as a hardliner, I would say that most of the problems that Ulrike Luxburg showed, like robustness and encoding information, or that we need so much data, are just temporary problems, and that in the future, the larger they get, the more we know about deep learning, etc., we won't have these problems anymore. And in the limit, deep learning will get to all of the things that we currently care about intelligence. So do we know of any properties that deep learning is never going to crack, no matter how much we understand about it?
Tough one. But I think if you define deep learning as including everything, deep learning is a solution. So this is a bit how like Max defined it. So I can't imagine not doing gradient descent on a model at the end. So in a sense, differentiable programming includes everything. So I tend to agree with you that, in fact, this is what Ule was saying. It's a bunch of open problems to be solved and research questions. And once those are solved, clearly progress will be made.
But, you know, one thing I often wonder is if you take simple models, it's not unreasonable to get guarantees, and we have many, right? So I think a question which I'm not really sure is, you can put a lot of modules where you have for which you have guarantees, put them together, then you start to, you know, optimize everything. Is there any hope that we can have some guarantees of the whole thing, or are we going to lose them? Maybe one day will be, you know, assuming for a second and having a theory is useful. Okay, so let's proceed by this crazy assumption. Then I thought it would be very hard to put together a huge system, differentiate through all, and still have a theorem. So we have to figure out the system engineering theory of machine learning, where you have all these blocks for which you have guarantees, and then you do some crazy optimization, you put it together. So I love differential programming as an idea, and as an algorithm design idea. I'm frightened as hell by it when I think of it in terms of a theoretician. How the hell you prove anything when you start to optimize over things? So, you know, I'm worried about that, and I wonder where does this stand in this discussion.
So, Simo?
Yes, so my question is that differential programming really a part of deep learning at all? Because differential programming was used in inverse problem back in 70s, 80s, and then, okay, it's a nice tool, and nowadays it's also used to train piecewise linear functions, but is it part of deep learning?
That's a tough, good question. I have another question, because we have a lot of optimizers in the room, and Lorenzo mentioned it. Can I replace the statement by "as deep learning made optimization obsolete," meaning that clearly to optimize a deep net, SGD works. Okay, fine. I think there starts to be proof of it, but now it leads to the illusion that if you throw gradient descent at any problem, it's going to work. Okay, and I think now I see this with students sometimes, that they say, oh, just like autodiff and run your favorite GD on it. But to me, there's still a lot of problems we can't optimize, and I'm afraid deep learning is like hiding the difficulty here, because it works on a very particular instance. So I don't know if anybody has a take on the survival of optimization. No, we're all dead. Okay. Julien?
Yeah, he's the one that has to answer this, right?
Yeah. I don't know. I mean, I was about to say that so differentiable programming is one of the nice principles from deep learning, which is kind of putting up also the rest of other approaches which are not necessarily deep. You know, we can think about many other types of approaches, sparse estimation with linear models. You know, you can do also differentiable programming with that. And this principle is like putting up the performance of all of the rest of machine learning. So in some sense, deep learning is very useful also for the other approaches. They are all going up together using these nice principles. Regarding optimization, we know it seems that we know very well how to optimize the current deep learning models, the ones from today. But when you apply differentiable programming to other types of problems, then there is lots of room for improvements, because you may apply SGD, it doesn't work. You apply SGD with Adam, it starts to work, you don't understand why. It seems that there is still, I would not say that optimization is dead. It's like differentiable programming is opening a lot of new problems that we need to solve. So there is, I think, lots of place to invent new things, new algorithms there. And also to invent algorithms where we understand as well the behavior.
Okay. Mario has an, thanks, Julien. Mario may have an answer to that.
I'm not sure I have an answer to that, but I think Simo had raised his hand before me.
But you go first, so that's fine.
Yeah, sure. So I was not going to answer that. Actually, I was going to well, it's connected to what Julian just said, but I was going to comment on maybe provoked by what Lorenzo said. So there's this famous paper about to understand deep learning, we need to rethink generalization. And maybe here we need, I would ask Lorenzo to define what he means by understand. Because I think when he says understand, he thinks he can prove a theorem, right? But maybe for deep learning, to understand deep learning, we need to redefine understanding, because maybe these structures are closer to biology than to engineering or to math. And so we need to think of understanding in the same way as a biologist thinks of understanding. So when a biologist says he understands some organism, he doesn't think about proving theorems. He thinks about having an idea about how it works based on some principles, but it doesn't really necessarily mean to get a quantitative theorem-like handle on the understanding. It could be something fuzzier. Do you think that's a way to go for deep learning? But that would be bad.
No, of course not. I mean, I'm totally biased, right? So I don't even have to hide myself. I think a problem that I find with this is that, even in the discussion, this is something I keep on repeating. Even in the discussion between in the Christmas Charol story, one goes from analyzing geophysics data to try to model imagination. I'm not sure, is deep learning an agent or is it a model? I think, if you're trying to shoot for super high goals like imagination or reasoning or something like this, and putting together, learning how to do super complex things, maybe, I don't know. It's so, I don't even know. I mean, it's hard for me to wrap my mind around the task. And maybe, yes, then you have to start to think about it in different ways. But if you think of, as I think about most machine learning as models, then you have to have theorems. And it's about as a guidance to drive, to design them, to understand them, to guarantee that they're going to do what they're supposed to do. And so my view as machine learning as models, understanding is, have math is part of the understanding. But somewhere there is this line between data science and modeling and, building AGI. And in this discussion, it's totally blurred. And that's for me, there's a distinction. And I think it's dangerous when you start to think of AI as an agent that is going to do something for you, and you just have to assemble together pieces. You offload the responsibility of models, which is something that scientists should never do. So to me, as a scientist, you have to have theory, you have to have practice, and you have to be responsible for your models. So it's very dangerous where you start to offload the responsibility of models to AI that it's an agent that is going to do it for you. So that's my take on it.
Okay. Thanks, Lorenzo. So we have a question by Simo, and then David.
Yes. So well, I commented about whether the differential programming belongs to deep learning. I don't know, but differential programming is actually very useful because you have a function, then you get the gradient, and I always use it when I implement quasi-Newton methods, for example, for optimizing all kinds of models and other good optimization methods. Well, sometimes I use gradient descent as well, but of course it's very obsolete, isn't it? And especially stochastic gradient descent is very obsolete optimization method. Oh, yes. So I like good optimization methods. How about you?
So you said that SGD is obsolete. Is it what you said?
I was provoking, yes. So isn't it a bit of like a obsolete method because it's just like a plain old gradient descent, and of course people have invented much better optimization during the 50 last years.
Sure, but at the end, nothing beats really AGD. Okay, well tuned, it's hard to beat. Yeah. So now we have David. You had a question. I don't see you.
Oh, yeah. I have a slight frustration listening. I'm a bit of an outsider to this, but I have a slight frustration listening to this debate. I mean, it was good that Max said that he wasn't really being honest in what he said, because I don't think, for me, there was nothing to be taken seriously at all in that type of presentation. What Ulrike said was very interesting. And I think the key problem everybody's facing just now is how to integrate scientific knowledge and how we do science with different types of machine learning approaches. And I think what I get frustrated with a discussion like this is you're talking about two things, sort of very kind of abstract things about AGI and machine learning in relation to that, and then very sort of technical details about how you do your particular neural network approach. While the real challenge, I think, that somehow it was definitely captured in what Ulrike was saying, and Max, I appreciate what Max did because he pushed her into this direction, but the real challenge is that idea of like, we know things in science, we have all of this information, that we have understood the world with humans, and then we want to have these deep learning methods and these other, sometimes it's just logistic regression, we want to have them to understand the world. And so maybe that wasn't, wait a minute, I've done this bad thing where I haven't asked a
I think I can answer something to your non-question anyway.
I wanted to hear more about that kind of thing.
Thanks, David.
So I think what David, and actually what Seymour before him also in a very different way, in almost orthogonal way, kind of pointed out, is this issue that maybe it's not, I mean, deep learning is just currently the most performant machine learning class of algorithms, maybe, right? So that clearly means that they are kind of, or at least for many applications, a really good choice. But they have these really annoying aspects, like that they are hard to train, that they're sort of the numerical aspects are really confusing, and also that they're hard to combine with other models, as David pointed out, which really come back down to this, like the issue at the core of this that Max kind of pointed out with his little thought bubble, that the key problem with these algorithms is that we don't fully understand them. So I guess a question posed to everyone else here is whether we will eventually just understand these models so well that they will become just like, I don't know, linear algebra is to us right now, something that can be fully understood, or whether they are fundamentally so hard that we will never get to a point where we understand them in the way that we understand scientific knowledge at the moment. I think that's a really hard kind of forward-looking question that we currently can't answer as a community, right? Or Max, was that what you were trying to get to with your, is deep learning the brain's way of explaining? No.
I think I'm trying to sort of wrap my brain around what's being said here and trying to figure it out. But I think I do see deep learning as a extremely useful methodology for scientific discovery, for building models. Sure, there is a problem with how to certify them. Coming back to Lorenzo's question, how do you prove things around them, or in practice, how do you even certify things, right? How do you build a brain, or how do you build a plane? Sorry, with a neural network, or self-driving car, perhaps, right? But there's other ways to test things, right? I mean, when we build chips or when we build planes, they are very complex systems, and we can definitely test them ad nauseum and still sort of certify them and get them into the world. And I don't think there is a huge difference with other models in that sense. So I certainly stand by the idea that deep learning is a very interesting set of tools that we should explore. I don't believe they're the answer to everything, and there's new ingredients that we need to incorporate. And certainly when you're interested in proofs and guarantees, this is not the way to go. But yeah, I'm trying to figure out what David was trying to say, and I can't quite figure
Maybe
out
I can,
what the critique
clarify,
is. And
clarify a bit more, because I don't feel either of those answers was close to what I was trying to say. I mean, what I'm trying to say is that the real problem, I think, is how you can use these new statistical methods that you have, how you can best use them in the traditional way of doing scientific analysis. And I think Ulrike touched on that at the end, and I'd just like to hear some more about that specifically.
I just want to say it's used a lot in scientific discovery right now.
Oh yeah, absolutely.
Yeah.
But
you think that's not the right way to go? I mean, if you
No, I do think it's the right way to go. I think it's absolutely the right way to go. I would say that it's a new statistical, or it's a part of a statistical tool that we can use in scientific discovery. And I would think that we would have to be investing most of our time with is how we use that in a sensible way, so that we can tell, if we already know some causal laws, how do we integrate those into models, rather than worrying about if our models can learn these causal laws. We can already do this causal reasoning. And so how do we best combine our own causal reasoning with the statistical reasoning that we get from these types of machine learning models? Does that make sense?
Yeah, it makes some sense to me, but maybe somebody else should also speak. But
thanks, Max and David. Well, Marius, as a last comment or question.
Yeah, it's a new question. It's no comment to the previous speaker. So, I mean, most of you, or many of you who were speaking so far are professors, and they can easily say, well, you know, deep learning works, but we also need theory, and we can just have one PhD student doing the one thing and one PhD student doing the other. But if you were now in the shoes of the students here, who can't sort of like put many eggs in different baskets, would you rather right now try to put your eggs in the deep learning basket, or put your eggs in the traditional machine learning basket and focus your own career on that if you had to restart your own career?
But what, I mean, sorry, but isn't that a bit extreme? I mean, if I think even just think about, I guess it depends a bit what is the timeline you give you and how much time you put. But let's say, if I think of a master for a year or even 6 months, where you can take 3-4 courses just to begin with, I think starting from basics and moving on is not a bad idea. So I guess the point here was, if we do a one course on basics of machine learning, so we just disregard logistic regression, SVMs, or basic optimization, just write in and a nitty-gritty way of put together a system, or should do that. So really, I mean, I hope your was a provocation. I just would like to answer the provocation before we move on to the question. But really, how much little time you have before you have to split yourself and make the decision to dump one or go for the other?
I mean, okay, so in your machine learning masters, you will learn all different kinds. But if you're a PhD, right, you will have to choose certain projects, and you probably won't, and you will have to specialize over time in your career. So
sure,
you can't just say, I do one paper on some theoretical model, and then a deep learning paper. Probably, maybe some people can, but most people can't. So if you were at the beginning of your PhD, let's say, or at the beginning of your research career, like which kind of path would you choose and why? Or maybe why do you think this is a bad question or distinction?
No. I was just trying to figure out what was the question.
I think this question is somehow, there is not just this one direction, right? I mean, I remember when I started to work on learning theory, I mean, machine learning was a very small field. And then everybody said, you know, there's going to be this one professor at a couple of universities, you need to work on application. You can't just work on theory. You're never going to get a job. I got a job. I never worked on applications. You know, and whatever advice we're going to give you, it is, there are going to be so many different positions which you can get in machine learning in the next 20 years. There's going to be room for people who do theory. There's going to be room for people who do deep learning. There's a whole range of things you can do. And I think whenever what you are doing, if you do that in a convincing way, that is going to be fine. And I think the decision is maybe rather, do I want to be in an area which is so hot that if I don't submit my preprint to archive today, but tomorrow then somebody else has done it or not? I mean, I think these are also the kind of decision. It's not just, do I need to work on deep learning or not? Many people are working on, I mean, also if you look at NeurIPS, there are many papers on deep learning, but there are also many papers on other topics. So I don't think you need to take a decision here. And also you don't, I mean, once you've taken a decision for now, it also doesn't mean you've taken this decision forever. You can work on something for a year and then you work on something else, or for 5 years, or whatever you like. I think really, this is a question that I know that troubles many PhD students, but I think it is not a question. Do good work in whatever you're doing and you're going to make your career.
So thanks a lot, Ule. This looks like a very good concluding statement for the debate, a positive statement. So I would like to thank a lot Ule and Max for all the work they put in. I think they created a very nice Christmas story. I can tell my kids next week. And so on this, I would like to thank also all participants, and I wish you happy holidays and good luck with your various confinements and lockdowns, and see you all next year.
Merry Christmas, everyone.
See you all.